Alright, let's dive straight into the fascinating world of ETA for VLSI. We're talking about the intricate dance of electrons and materials that powers our digital lives. So, what is VLSI? Very large-scale integration. Think about it. From the first integrated circuits with just a handful of transistors back in the 90s, we've exploded to billions on a single chip today. This isn't just about making things smaller, it's a relentless march of innovation. We've seen the classic scaling, where we just shrink everything, then move to effective scaling, trying to keep performance up while shrinking, and now we're in hyperscaling, pushing the boundaries with new materials like silicon-germanium channels, and entirely new architectures like FinFETs and gate-all-around. It's a technological arms race, constantly pushing the limits of physics and engineering. The graph here shows this incredible journey. Look at the transistor counts. It's mind-boggling. And notice the materials evolving. Silicon-germanium, germanium channels, high-K dielectrics, metal gates. It's all part of this quest for better performance and lower power. At the heart of most modern chips are MOSFETs, metal oxide semiconductor, field effect transistors. These are the tiny switches that make everything happen. The name itself tells you the layers. Metal, usually polysilicon these days. Oxide, typically silicon dioxide, acting as an insulator, and semiconductor, usually silicon. The gate controls the flow of current between the source and drain. By applying a voltage to the gate, we can turn the transistor on or off, controlling the flow. It's the fundamental building block of digital logic. Understanding this simple structure is key to understanding how complex circuits work. Now, let's talk about the materials. Why do some materials conduct electricity and others don't? It all comes down to electrons. Inside an atom, electrons orbit the nucleus in shells. The outermost shell, the valence shell, determines how the atom interacts with its neighbors. Atoms try to fill their outer shells by sharing electrons, forming covalent bonds. Think of silicon atoms holding hands. If you remove electrons, you get ions, positive charges. For a material to carry current, it needs free electrons that can move around. Resistivity measures how hard it is for electrons to flow. Look at the silicon crystal structure, each atom sharing electrons with 4 neighbors. And the energy band diagram shows the energy levels electrons can occupy. The gap between the filled valence band and the empty conduction band is crucial. First up, insulators. These are the materials that resist electricity flow. Think of them as the bouncers at the club door for electrons. They have very strong covalent bonds, meaning electrons are tightly held, not easily freed. You need a huge force to knock an electron loose, and even then, it might just stay on the surface. Materials like silicon dioxide, which is CO2, are our go-to insulators in VLSI. Why? Because they're excellent electrical isolators. They prevent different parts of your circuit from shorting out. Look at the energy band diagram. The gap between the valence band and conduction band is huge, over 3 electron volts. Electrons just can't jump across that gap easily. That's why insulators are insulators. Next, conductors. These are the highways for electrons. Metals like aluminum and gold are prime examples. They have lots of free electrons that can roam around freely. Imagine a crowded street where people can move easily. When you apply a voltage, these electrons flow, creating current. The ease of this flow is related to how many electrons there are, how wide the path is, and how easily the electrons can move, which is called mobility. Conductors have very low resistivity, sometimes almost zero, like superconductors. In our chips, they're used to connect all the transistors and components. Again, check the energy bands. The gap between the filled valence band and empty conduction band is basically zero. Electrons can jump into the conduction band easily, making them great conductors. And then there are semiconductors. These are the interesting ones. Their resistivity is somewhere in between, typically from 10 to the power of -3 ohm centimeters to 10 to the power of 7 ohm centimeters. Pure silicon, or intrinsic silicon, is a semiconductor. What makes it special is that it conducts electricity using two types of carriers: free electrons and holes. Think of it like this. When a silicon bond breaks at room temperature, it releases an electron, but it also creates a vacancy, a hole. This hole acts like a positive charge carrier. So, for every free electron created, there's a corresponding hole. They always come in pairs. This dual carrier nature is fundamental to semiconductor behavior. The diagram shows this beautifully. Breaking a bond releases an electron and leaves a hole. Now, pure silicon isn't always ideal. We often want to control the type and number of carriers. That's where doping comes in. We introduce tiny amounts of other elements, impurities, into the silicon lattice. Phosphorus has 5 valence electrons, one more than silicon. When you put phosphorus into silicon, that extra electron is easily freed up, becoming a free electron carrier. This makes the silicon N-type, meaning N for negative, dominated by electrons. Boron, on the other hand, has 3 valence electrons, one less than silicon. When boron replaces a silicon atom, it creates a vacancy, a hole, which becomes a positive carrier. This makes the silicon P-type, P for positive, dominated by holes. By carefully choosing and placing these dopants, we can tailor the semiconductor's properties exactly as needed for transistors. Look at the diagrams. Phosphorus adds electrons. Boron creates holes. This is how we build the p-n junctions that are the heart of diodes and transistors. Let's zoom in on the quantum world inside these materials. Electrons and atoms exist in specific energy levels, like steps in a ladder. When atoms join together to form a crystal, these individual energy levels broaden into bands. There's the filled valence band, the nearly empty conduction band, and the forbidden gap in between. Electrons can only jump into the conduction band if they gain enough energy, usually from heat or light. This concept of energy bands is absolutely fundamental to understanding why materials behave as conductors, insulators, or semiconductors. It dictates how easily electrons can move, and thus how well the material conducts electricity. A key concept in semiconductor physics is the Fermi level. Imagine you're filling a stadium with fans, starting from the lowest seats. At absolute zero temperature, all the electrons would be packed into the lowest available energy states. The highest energy level occupied by an electron is the Fermi level. It's like the dividing line between the occupied and unoccupied states. This level is crucial because it tells us about the material's conductivity and how it responds to external factors like voltage and temperature. It's the reference point for electron distribution. So, what happens to the Fermi level at absolute zero? Well, since all electrons are packed into the lowest energy states, the Fermi level sits right at the top of the valence band. It's the boundary. If you calculate the probability of finding an electron below the Fermi level, it's 100%. If you calculate the probability of finding an electron above the Fermi level, it's 0. The Fermi level is the sea level for electrons, below which they are all present, and above which none are. This is the simplest case, the baseline. Now, let's bring it to room temperature, about 300 Kelvin. Things get a bit more interesting. Electrons gain thermal energy and can jump into the conduction band. The Fermi level shifts slightly. For pure silicon, the intrinsic semiconductor, the Fermi level is roughly in the middle of the forbidden gap. This means there's a roughly equal chance of finding an electron in the valence band or the conduction band, though the actual probability is less than 1 for either due to the exponential nature of the Fermi function. When you add dopants, extrinsic semiconductors, the Fermi level shifts significantly towards the conduction band for N-type silicon, indicating more electrons, or towards the valence band for P-type silicon, indicating more holes. This shift is what allows us to control the conductivity precisely. Let's look at the MOS capacitor, a fundamental component. It's basically a capacitor made of a metal gate, an oxide layer, usually silicon dioxide, and a semiconductor substrate. The energy band diagram shows the alignment of energy levels. Key concepts here are electron affinity, which is the energy needed to pull an electron from the conduction band edge into vacuum, and the work function, which is the energy needed to pull an electron from the Fermi level in the metal into vacuum. These differences in energy levels drive the behavior of the MOS structure when you apply voltages. The gate and body together form a capacitor. How does it work? It has three main operating modes depending on the voltage applied to the gate relative to the body. First, accumulation. Apply a negative voltage to the gate. This pulls electrons from the semiconductor body towards the oxide interface, accumulating them there. Second, depletion. Apply a positive voltage, but not enough to turn the channel on. This repels the majority carriers, holes in p-type silicon, away from the interface, creating a depletion region, an area depleted of charge carriers. Third, inversion. Apply a sufficiently large positive voltage, exceeding the threshold voltage Vt. This pulls enough minority carriers, electrons in p-type silicon, to the surface to form a conductive layer, the inversion layer, which acts as the channel for the MOSFET. These three modes are the basis of MOSFET operation. Let's visualize depletion and inversion. In depletion mode, applying a positive gate voltage pushes the holes away from the silicon surface, leaving behind a region depleted of charge carriers. This region acts like an insulator. Now, if you increase the gate voltage further, past the threshold voltage, you start pulling electrons from the bulk silicon to the surface. Enough electrons accumulate to form a conductive layer, the inversion layer. This layer is the channel that allows current to flow between the source and drain when the MOSFET is turned on. It's the transition from depletion to inversion that creates the switching action. Here's the MOS structure under accumulation. Look at the cross-section and the energy band diagram. With a negative gate voltage, the Fermi level in the semiconductor bends upwards, closer to the conduction band. This means the conduction band edge is lower than the Fermi level in the bulk, so electrons are pushed towards the oxide interface. The depletion region is minimal, and the surface is rich in majority carriers, holes in this p-type example. The bands bend upwards, indicating the accumulation of negative charge, electrons, near the surface. Now, apply a small positive gate voltage. We enter the depletion region. The energy band diagram shows the conduction band edge bending downwards, moving away from the Fermi level. This means the conduction band is higher than the Fermi level near the surface, so electrons are repelled. The majority carriers, holes, are pushed away from the surface, creating a depletion region. The width of this depletion region depends on the gate voltage. The bands bend downwards, indicating the removal of charge carriers from the surface. Increase the gate voltage significantly. Now we're in inversion. The energy band diagram shows the conduction band edge bending down quite a bit, crossing the Fermi level in the semiconductor. This means the conduction band is now below the Fermi level near the surface. Electrons are pulled from the bulk into the surface, forming the inversion layer. This layer is conductive, allowing current to flow if connected to source and drain regions. This is the state where the MOSFET is turned on. The bands bend significantly downwards, indicating the formation of the inversion channel. Different materials have different properties. This table compares three common semiconductors: silicon, germanium, and gallium arsenide. Notice the bandgap energy, E sub G. Silicon has a bandgap of about 1.1 electron volts, germanium about 0.7 electron volts, and GaAs about 1.4 electron volts. A wider bandgap generally means higher breakdown voltage and better performance at high temperatures, but also harder to dope. Effective mass tells you how easily electrons and holes move. GaAs has much lighter effective masses, leading to higher electron mobility. Intrinsic carrier concentration, N sub I, tells you how many free carriers exist in pure silicon. These numbers are critical for designing devices. For example, GauZ is often used for high-frequency RF devices because of its high electron mobility. Okay, we know the basics of the materials and the fundamental transistor. How do we actually build these incredibly complex circuits? Fabrication of CMOS ICs involves creating layers of materials, patterning them with microscopic features. Modern processes can achieve feature sizes below 0.12 micrometers, that's 120 nanometers. We can pack over 100 million transistors onto a single chip. This isn't cheap, it's decades of research and development. Silicon is arguably the most studied element on Earth because of its importance. We'll now look at the manufacturing process, focusing on the aspects relevant to VLSI design. It all starts with the wafer. These are large circular discs of silicon, typically 100 to 300 millimeters in diameter. Think of them as giant cookies where we bake the circuits. Each wafer can contain hundreds or thousands of individual circuits, called dies or die sites. The flat edge on the wafer is a reference point for aligning the patterns. Some wafers have notches or other flats to indicate crystal orientation. The process involves thousands of steps, starting with a bare, polished silicon surface. The image shows typical wafer sizes and orientations. Silicon wafers come in different crystal orientations, mainly 100, 110, and 111. The 100 orientation is the most common for advanced ICs because its surface atoms are arranged in rows, which helps with growing uniform layers and creating sharp patterns. It's great for high-performance transistors. The 110 orientation is less common but useful for specific applications like MEMS. The 111 orientation was used historically and has advantages for certain analog circuits due to lower interface states and potentially higher carrier mobility. The choice of orientation depends on the specific application requirements. The pictures show examples of different wafer types. Not every chip on the wafer works perfectly. Manufacturing is complex, and defects can occur. Yield is a critical metric in VLSI. It's simply the percentage of functional chips produced from a batch. Look at the diagram. If you have 22 sites, and 12 are good, the yield is 12 divided by 22, which is about 55%. A high yield is essential for profitability. An 85% yield means 85% of the chips are usable. Improving yield is a constant goal in semiconductor manufacturing. It directly impacts the cost of the final product. Building a chip is like building a skyscraper with multiple floors, each made of different materials. We stack layers of silicon dioxide, silicon, metals, etc. in precise sequences. Most layers are deposited first, then patterned using lithography. Doped silicon is an exception, often doped during the lithography process. Silicon dioxide, SiOR, is super important. It's an excellent insulator, sticks well to silicon, and can be grown directly on silicon or deposited. It's the workhorse for gate oxides and isolation layers. It's often called quartz glass or just glass. So, what exactly does SiOR do? It's incredibly versatile. Its high dielectric strength and constant make it perfect for capacitors and the gate oxide in MOSFETs. It acts as a barrier, isolating different transistors or parts of a transistor from each other. It also protects the delicate silicon junctions from moisture and other contaminants in the air. Basically, it's the glue, the insulation, and the protective shield in the chip. Without it, modern electronics wouldn't work reliably. How do we create these silicon dioxide layers? One way is oxidation. This process serves several purposes. First, it passivates the silicon surface, creating a protective oxide layer. Second, it acts as a mask. By covering certain areas of silicon with a mask, like nitride, and then exposing the wafer to oxygen, we can grow oxide only in the exposed regions. This allows us to selectively dope silicon in specific areas. This masking ability is crucial for creating the complex patterns needed for transistors and interconnects. There are two main ways to grow oxide: dry oxidation, and wet oxidation. Dry oxidation uses pure oxygen gas. The reaction is simple. Si plus OR yields SiOR. A silicon atom reacts directly with an oxygen molecule. This method is great for growing thin, high-quality oxide layers with a low density of defects and a high breakdown voltage. It's also preferred when you need to avoid contamination, especially sodium ions. However, it grows relatively slowly. Think of it as a slow, steady process. Wet oxidation uses steam, HRO vapor. The reaction is Si plus RHR, O yields SiOR plus RHR. Water vapor reacts with silicon to produce oxide and hydrogen gas. This process is much faster than dry oxidation, especially at lower temperatures. It's often used to grow thicker oxide layers. However, the quality of the oxide grown by wet oxidation is generally lower than that from dry oxidation. It's like using a faster, but maybe less refined, method. Here's a comparison of the growth rates. Look at the table. At 900 degrees Celsius, wet oxidation grows about 100 nanometers per hour, while dry oxidation is only 19 nanometers per hour. At 1100 degrees Celsius, wet oxidation hits 630 nanometers per hour, while dry is 120 nanometers per hour. Wet oxidation is significantly faster, especially at higher temperatures. However, remember the trade-off: speed versus quality. Dry oxidation gives you a better, denser, higher breakdown voltage oxide, but it takes longer to grow. Process engineers choose between them based on the specific layer needed. This diagram shows the oxidation process. On the left, you see the silicon wafer being exposed to either oxygen or steam. The oxide grows, consuming silicon atoms from the surface. The ratio of consumed silicon to grown oxide is roughly 0.46. The right side shows the equipment, typically a furnace with quartz tubes and boats holding the wafers. Gases like oxygen or steam, sometimes mixed with nitrogen or hydrogen chloride, flow through the system. This controlled environment allows for precise oxide growth. Besides silicon dioxide, another important material is silicon nitride, SiS-N-N-SU. It's often formed by reacting silane gas, SiH-Si, with ammonia gas, NH-SN. Nitride is also used for insulation, but it has a higher dielectric constant than oxide, about 7.8 compared to 3.9. This makes it useful for creating oh-no-no structures, oxide-nitride oxide sandwiches, which are used in capacitors, especially in DRAM memory cells. It's also a good barrier against diffusion, protecting underlying layers. It's another key player in the semiconductor toolkit. Polycrystalline silicon, or polysilicon, is another vital material. Unlike single crystal silicon, which is perfectly ordered, polysilicon is made of many small, randomly oriented silicon crystals, like grains in a polycrystalline metal. It's often used as the gate electrode in MOSFETs because it's easier to deposit and pattern than single crystal silicon. It's also used as a sacrificial layer or for other structural purposes. The image shows the difference between single crystal, polycrystalline, and amorphous structures. Metals are crucial for connecting everything together. Aluminum is the classic choice for interconnects. It's easy to deposit, adheres well, and has decent conductivity. But aluminum has a nasty problem called electromigration. When current flows through a narrow aluminum line, especially at high current densities, the metal atoms themselves can start to migrate, moving from the cathode to the anode. This creates voids, pits, where atoms leave, and hillocks, bumps, where atoms pile up. These defects can break the wire or cause shorts, leading to chip failure. It's a major reliability concern. To combat electromigration in aluminum, a common solution is to mix copper with aluminum, creating aluminum-copper alloys. This significantly reduces electromigration but increases the resistivity slightly. Another way to manage electromigration is through design. By controlling the current density, J, which is current divided by cross-sectional area, we can prevent excessive atom movement. Since the thickness T is fixed by the process, designers must ensure the width W is large enough to keep J below a critical value J max. This leads to minimum linewidth rules in design. Also, aluminum requires high-temperature processing, which can be problematic for some advanced nodes. Alternatives like tungsten, copper, or silicides are explored for gate terminals and interconnects. Doping silicon is essential. We start with a silicon wafer, which is already doped N-type or P-type. To create the active regions of transistors, we need to introduce specific dopants in precise locations. Two main methods are used. Diffusion involves heating the wafer in the presence of a dopant gas. The dopant atoms diffuse into the silicon, with concentration decreasing as you go deeper. The profile depends on temperature and time. Ion implantation is more precise. Dopant atoms are ionized, accelerated, and shot into the silicon with a beam. The concentration profile is peaked near the surface, determined by the ion energy and mass. The diagrams show the difference. Diffusion spreads out, implantation is more localized. Ion implantation is a sophisticated technique. Dopant atoms are first ionized in a chamber. Then, they're accelerated to high energies, typically 20 to 200 kilovolts, using a particle accelerator. The beam scans the silicon wafer. The ions penetrate the surface and come to rest after colliding with silicon atoms. The depth of penetration is controlled by the ion energy. A mass separator uses magnetic fields to select the desired ion species, filtering out unwanted ions. This allows for very precise doping of specific areas. The diagram shows the complex setup: ion source, mass separator, lenses, accelerator, and deflection plates to steer the beam accurately onto the target wafer. When those high-energy ions slam into the silicon, they don't just sit there. They collide with silicon atoms and electrons, losing energy and eventually coming to rest. This process damages the silicon crystal lattice. To repair the damage and allow the implanted dopant atoms to settle into proper positions in the lattice, we perform an annealing step. This involves heating the wafer. During annealing, the dopants also diffuse slightly, spreading out a bit. This diffusion is important for achieving the desired final dopant profile. After implantation and annealing, we often need to make the wafer surface flat again, which brings us to chemical-mechanical polishing. As we build up layers, the wafer surface can become non-planar. Imagine depositing a layer of polysilicon, then oxide over it. The oxide layer will follow the contours of the polysilicon. If you deposit metal on top, it will follow the oxide's contour, potentially getting wider and thicker. Add more layers, and the surface gets progressively rougher. This roughness can cause problems for subsequent lithography steps. Chemical-mechanical polishing, or CMP, is the solution. It uses a combination of chemical etching and mechanical abrasion to polish the surface flat. Step 1 shows oxide deposition. Step 2 shows etching. Step 3 shows metal deposition. And Step 4 shows CMP to flatten the surface. CMP is crucial for maintaining planarity in advanced processes. Creating the intricate patterns on each layer is arguably the most critical challenge in modern CMOS fabrication. This is done using photolithography, a process similar to making photographic prints. We start with a computer file defining the pattern. This data is used to create a reticle or mask, a piece of high-quality glass with the pattern etched onto it using a metal like chromium. The reticle is typically 5 to 10 times larger than the actual chip pattern. It has transparent and opaque regions. The image shows a simple reticle pattern. To transfer the reticle pattern onto the silicon wafer, we first coat the wafer with a light-sensitive material called photoresist. Think of it like photographic film. We spin the wafer rapidly, using centrifugal force to spread the resist evenly into a thin film. There's usually a thicker edge bead near the wafer's edge due to surface tension. The resist is sensitive to ultraviolet light. The diagram shows the spin coating process, resulting in a uniform resist layer ready for exposure. Next comes the exposure step. The reticle, with the pattern, is placed above the resist-coated wafer. UV light passes through the transparent parts of the reticle, projecting the pattern onto the resist. The resist is sensitive to this UV light. After exposure, the resist is developed using a chemical rinse. Most VLSI processes use positive resist. In positive resist, the areas exposed to light become soluble and are washed away during development. The areas shielded by the opaque parts of the reticle remain hardened and insoluble. The diagram shows the exposure and the resulting patterned resist after development. Negative resist works the opposite way. Exposed areas harden and shielded areas dissolve. Positive resist is more common for fine features. Let's recap the photolithography steps. We start with the reticle, the master pattern. We coat the wafer with photoresist. We expose the resist using the reticle and UV light. We develop the resist, removing the exposed or unexposed areas depending on the resist type. This leaves a patterned resist layer on the wafer. This resist acts as a stencil for the next step. Applying the photoresist is crucial. As we discussed, spinning the wafer ensures a relatively uniform coating. The resist must be applied precisely and uniformly to get accurate patterns. Any imperfections in the resist layer can lead to defects in the final pattern. The diagram shows the spin coating process again, highlighting the uniform resist layer and the edge bead. The exposure step is where the magic happens. The reticle pattern is projected onto the resist using UV light. The shadow cast by the opaque parts of the reticle defines the pattern transferred to the resist. The diagram shows the light passing through the reticle and creating the shadow pattern on the resist. The quality of the optics and the cleanliness of the reticle and wafer are paramount here. Even tiny dust particles can ruin the pattern. After developing the resist, we have a patterned resist layer. This hardened resist now acts as a mask. We perform an etching step, typically using reactive ion etching, RIE. This involves bombarding the wafer with a plasma containing reactive gases. The plasma attacks the material underneath the resist, removing the unprotected areas. The resist itself is resistant to the etchant. So, the etched pattern mirrors the resist pattern. The diagram shows the oxide being etched away in the areas not covered by the resist. This transfers the pattern from the resist to the underlying material. For doped silicon, the sequence is often reversed. Oxide is grown, then patterned and etched to expose the silicon for implantation. For creating doped regions, we use the resist oxide mask to protect the silicon during ion implantation. We define the areas where we want to implant dopants using the resist mask. Then, we perform the ion implantation step. The ions only penetrate the silicon in the areas where the resist and oxide mask are absent. This creates precisely defined doped regions, like the N+ regions shown in the diagram. This is how we create the source and drain regions of a transistor. Photolithography is incredibly sensitive. Even the smallest speck of dust landing on the reticle or the resist can cause a defect. A particle on the reticle can be imaged onto the wafer, creating a flaw. This is why lithography is performed in clean rooms. These facilities use HEPA filters to remove particles from the air. Class 100 clean rooms mean fewer than 100 particles per cubic foot greater than 0.5 microns. Workers wear special suits, bunny suits, and take air showers before entering. Automation with robots is also common. Maintaining extreme cleanliness is essential for high yield, especially at submicron geometries. What kind of contamination are we talking about? There are three main types. Molecular contamination comes from outgassing, vapors, oils, solvents, paints, glues, epoxies, aromatics. If you smell something, it's likely contamination. Surface contamination includes fingerprints, skin oils, creams, waxes, polishes. People are a major source of particulate contamination, shedding skin, hair, lint from clothing. Other sources include particle-shedding materials like cardboard boxes and paper, and activities like drilling, sawing, or sanding. Everything needs to be controlled. Most particles that cause trouble are incredibly small, often invisible to the naked eye. They are typically measured in microns, or even nanometers. Their small size means they can easily stick to surfaces due to electrostatic forces. The diagram compares particle sizes. 0.5 microns is the standard size counted in clean rooms, while human hair is about 100 microns. So, the particles we worry about are about 100 times smaller than the thinnest hair. Controlling these tiny particles is a massive undertaking. This chart gives a sense of scale. Common airborne contaminants range from ions and molecules to viruses, bacteria, smoke particles, and larger dust particles. The critical size for cleanroom control is around 0.5 microns. The diagram on the right shows the impact of a fiber on a mask during lithography. Even a tiny fiber can block light, causing a defect in the pattern transferred to the wafer. This highlights the importance of controlling all sources of contamination. Workers in cleanrooms wear specialized bunny suits. These coveralls, hoods, gloves, shoe covers, and masks are designed to prevent shedding fibers and particles. Cotton is avoided because it sheds lint. Synthetic materials like polyester are preferred. The sequence of putting on the suit is critical to avoid contamination. The diagram shows the proper attire. Every detail matters in maintaining the required cleanliness level. Clean rooms also control airflow. There are two main types of airflow patterns. Unidirectional, or laminar flow, means air moves in parallel streams at a uniform velocity, typically downwards. This pushes particles away from the work area. Class 100 and below clean rooms often use this. Non-unidirectional or turbulent flow involves recirculating air with varying velocities. Class 1000 and 10,000 clean rooms often use this. Mixed patterns combine elements of both. The choice depends on the required cleanliness level and the specific process needs. These diagrams illustrate the difference. The turbulent clean room on the left recirculates air, potentially mixing contaminants. The laminar flow cleanroom on the right uses HEPA-filtered air moving in parallel streams, effectively sweeping particles away. Laminar flow provides superior cleanliness, but is more complex and expensive to implement. The choice depends on the criticality of the process. Let's revisit field oxide. It's that thick layer of silicon dioxide grown on the silicon substrate. Its primary job is isolation. It electrically separates different active regions of the chip, preventing unwanted interactions between adjacent transistors. This is crucial for the proper functioning of the circuit. It's thicker than the gate oxide, which is directly under the gate. The diagram shows the field oxide surrounding the active regions where the transistors are built. Why is field oxide so important? Three main reasons. Isolation. It electrically separates the active regions, preventing crosstalk. Reduction of parasitic capacitance. By providing a thick insulating layer between regions, it minimizes unwanted capacitance between conductive parts, improving speed and reducing power consumption. Minimizing leakage currents. It acts as a barrier, reducing unwanted current leakage between isolated regions, especially when the device is supposed to be off. All these contribute to better device performance and reliability. How do we create this field oxide? Historically, LOCOS, local oxidation of silicon, was used. It involves selectively growing a thick oxide layer in specific regions. The diagram shows the bird's beak effect. When you try to grow oxide only in certain areas, protected by a nitride mask, the oxide tends to grow laterally under the nitride edge, encroaching into the active region. This reduces the usable area for the transistor and limits scaling. It's a significant drawback of LOCOS for dense VLSI circuits. To overcome the limitations of LOCOS, shallow trench isolation, or STI, is now the standard. Instead of thermally growing oxide, STI involves etching trenches into the silicon substrate and then filling them with deposited oxide. This provides much more precise isolation. The diagram shows the STI process. Trenches are etched, filled with oxide, and then polished flat. It's particularly important for feature sizes below 250 nanometers. Why is STI so important? It enables high-density integration. Because the trenches are filled, they don't encroach into the active regions like LOCOS does. This allows for much denser packing of transistors. It also reduces parasitic capacitance more effectively, leading to better performance. And it minimizes leakage currents between devices. STI is essential for modern, high-performance, low-power VLSI. So, what are the key benefits of STI? Scalability. It allows continued shrinking of transistors. Improved planarity. The CMP step after filling the trenches creates a flat surface, crucial for subsequent layers. Reduced bird's beak effect. No more oxide encroachment. Enhanced device performance. Lower parasitic capacitance and leakage lead to faster, more efficient devices. In summary, STI is a cornerstone technology for advanced CMOS fabrication, enabling the incredibly complex chips we rely on today.